So the 4, 6, and 9. Okay, quiet, please. Quiet, please. So remember, we have strategies for doing these that don't involve actually following the algebra, which is you could have stored a value for x. What value do we recommend? Pi. And then just put this in the calculator to see the decimal value. All right, and then you go through these and find the decimal values and which was the correct. It ended up being this one right here. Now, math-wise, to add or subtract radicals, they got to be the same radical. And these are square roots, but what's inside the radicand is not the same. But you can simplify. This is 75 is 25 times 3, and 27 is 9 times 3. So eventually, they will simplify so that they actually are the same radical, the square root of 3x, the square root of 3x. Now that they're the same radical, how do you combine, add, or subtract radicals? You combine the coefficients. So 5x minus 3x is 2x. Okay. How many of you did that by solving it? And how many did it by the storing of values? You did? Okay. That's why you want to practice that now, right? If you tried to do it, quiet please, if you tried to do it by storing values and didn't get it right, I mean, now's the time to figure out, how do you do that correctly, right? The next one, again, here you had 2 variables. So what did you store for the second variable? E, right? What do we mean by E? What is E? Okay. You staying? You staying? Okay. Remember that if you have one variable to store, then pi works. Pi is above the caret sign right there. Second that. If you're going to store it for 2, like this one, we got to store for x and y, then right underneath that button and above to the left, there's the lowercase letter e. What is the lowercase letter e? What does it represent? Thank you. Okay, we've used this in class before. What is E? What does it represent in math? You guys need to be thinking a lot harder. The base of the natural logarithm. Okay? So recommend use E. It's got to do for 2. Now, if you had to do for 3, I don't know, make something up. I don't think you'll have to do for 3. So if you store that way, then you could pick it out. Did you pick out which was the right one? Which was the right answer here? Shane? It should have been D, right? If you did it with the math, I mean, again, this was the converting from radical to rational exponent, right? That's 16 to the 1/4, because that's what the 4th root means. It's x to the 15 over 4, y to the 17 over 4. And the 6, if you did it just like that and you didn't recognize your answer there, well, then just do 16 to the 1/4. The 4th root of 16 is 2. That's why it's D. And again, you would have to store for 2 variables and then go through them. What did you get for an answer? The right answer was C, right there. Now, if you simplified, first it was a convert, right? Convert from the rational exponent to a radical. It just that the 7th root of y to the 36th can be simplified, right? You could break it up into y to the 35th times y, and then the 7th root of y to the 35th is y to the 5th. That's why they get this right here. The y to the 5th came out. There was still a y left inside. The x to the 3rd was always inside. I mean, you should have recognized right away that like A and B, they can't be it, right? Because they're not 7th roots. It had to be a 7th root, so it wasn't going to be either one of these. It had to be one of these, and it was C. Now, number 8, which I didn't ask you to do, but just to show you, I mean, here's one where you have to simplify a radical, like we did in the homework last night, like we could have done on any of the other 3. But those other 3, you actually had the option to store a value for the variables and then to see which one was the same. This one, you kind of don't, but you kind of do. Because in the end, if you do, once you work this thing out and you've put the correct factors in here, you can always do that to see if you're right. Right? If you put your answer in here and you store for X and you store for Y and you see what the decimal value is, it better be the same as that. Right? So, I mean, I don't know if you'd want to like guess and check there. There'd be a lot of guessing and a lot of checking. But still, I mean, how do we simplify this one? Is 162 a perfect cube, since this is a cubed root? No. Does it have any factors that are perfect cubes? And which would you say is the factor that is a perfect cube? 27. So remember, if you're not great at that, clear, you can always, use your calculator to make the perfect squares and perfect cubes. Since we're just interested in perfect cubes now, I'm going to put an x to the third, right, enter, and then go to the table of values. And look, these are all your perfect cubes. And you can see that it goes from 125 to 216, jumps right over 162, so that's not a perfect cube. So you have to start with the biggest number possible if you have to. Right? You could say 162 divided by 125 doesn't divide in evenly. 162 divided by 64 doesn't divide in evenly. 162 divided by 27, what do you get? 6. So there you go. So that's how you want to break this one up. You're going to break it up into 27 times 6. Now, do you need to split up the x to the 6th? No, it's good, right? Because 6 divided by 3 goes evenly. Just leave that as an x to the 6th. And the y to the 7th? How are you going to split it up? Y to the 6 times y. It's kind of like the one we just did over there. Y to the 6 times y. So then we're going to go through and take the third root of all of those. Right, the third root of 27, 3, times the third root of 6. The third root of x to the 6th, what is it? X squared, right? It's 6 divided by 3, x squared. The third root of y to the 6th is y squared, and the third root of y. So the answer is 3x squared y squared times the third root of 6y. So this is one of those technology enhanced items. You would have had to drag the 3 over here, then drag the x squared over here, and the y squared over here. And then we're going to drag in a 6 here, and y here. So that'll look like 3x squared y squared times the third root of 6y. Again, let's say you, whatever you get at that spot, you could always store a value for x and y and see if that does not equal that. Right? I mean, at least you could use it to check. Okay, then we get to solving equations. And we're going to solve all these the right way. But if you had to solve them by using a strategy, a multiple choice, solve an equation, what is the first thing you'd think of? John? No, what would you do if you just wanted to not solve it the way we learned to solve it? Just plug in one at a time until you find the one that works, right? I mean, you always have that option on any equation which is a multiple choice. Just keep storing or substituting x equals these numbers until you find which one works. Now, I would recommend if you're going to do that with this kind of problem, use this store function to do it. Like in this case here, I could say 67 over 8 store x, right? And then type in this expression just like you see it. The square root of x minus 1 plus 4 and see whether it equals 8. The reason I would say use that is because what if you have negatives? What if you have squares going on? Things that we would likely make mistakes in order of operations and whether or not negative 4 squared is positive or negative, you won't have any issues like that. If you just store this value for x and then evaluate that expression. If it equals 8, you found your answer. If it doesn't, then restore 61 over 8 equals x, right? And then keep doing it until you get the right answer. So I think you're familiar with that. What's another strategy? Kind of a strategy, but kind of not. Okay, well, I would call that's math, right? How do we solve this with math? Yeah. Okay. So remember this, the steps are isolate the radical and then undo the radical. In this case, subtract 4. So you got the square root of 8x minus 1 equals 4. And then how do you undo a square root? You square both sides, right? So this is squared and squared. So 8x minus 1 equals 16. And now you have a pretty simple algebra equation, right? Add 1, divide by 8. The answer is there. But there's one other way you've got to solve this, which in a way is it's not solving it like that, and it's not quite the strategy of just substituting everything until it works. But it's actually a pretty good. Right. You could solve it as a system. Put on the first line, y1, the square root of 8x minus 1 plus 4. And then put on the second line, y2 equals 8. And then what would you be looking for on the graph that would tell you the intersection point? That'll be the answer, right? Looks like this. Clear. So the square root of 8x minus 1 plus 4. Okay? And then the other side of the equation goes on line 2. Right? So that is 8. And when I look at the normal zoom, you could see both graphs. Do you see where they intersect? Okay, where they intersect the x value, not the y value, because we introduced the y values. There were no y values here. But whatever is this x value, that's the answer. How do we find the intersection point? Second trace, 5 for intersect. And then notice this, because if you're going to use this strategy, you've got to be watching for this. Notice that it's got this curve up there, but what's the point on the curve? X equals 0, and there is no y. If you try to hit enter to say pick that, it keeps coming back to the first curve because it's not actually on the curve yet. So arrow over until you get a y value. Okay, now you're on the first curve. You weren't on the first curve when you started. Now when you hit enter, it pops to the other one, and then it says you want to guess. Sure, guess. And the answer is 2.125. So how can you recognize that as a fraction? Yeah, you could do math, enter. 2.125. Enter. Oh, sorry. Second, enter. Math, enter. 17 over 8. Or you could turn these into decimals until you find the right one, right? So remember that as a strategy for solving equations that would work for any kind of equation. As long as the intersection is on the screen, that should work. Now, you'd probably have to want to practice it, especially for rational equations. It's a little different because all the vertical asymptotes can throw it off a little bit, but it will still work. It will always work. Okay, so try to do 17, 21, 23, 24. And they're all solved equations. So any way you can, I'm going to stop. Okay, let's go. Attention, please. So again, you have the option to store for x or plug in for x and just see which one works. If you were to solve it, remember to solve a radical equation, first you isolate the radical, but in this case it already was. and then you undo it. How do you undo a cubed root? You cube both sides, right? And you cube 2, you get 8. So that's the solving of it. Should have been C. Should have been C. Yeah, a lot of these, as Curtis is saying, if you know how to do the math, it takes like 30 seconds. If you want to start solving, storing all 4 of them until you get it, you might be doing it about 5 minutes. But it's okay. Get it right. Again, this one we did have to take a step to isolate, so we subtract 11. And then how do you undo a 4th root? You raise to the 4th power, right? So 3 to the 4th is 81. 3 to the 4th is 81, so 81 plus 4 is 85. Okay, this one, again, this is a proportion. And if you have a proportion, which means a fraction equals a fraction, then it always works to cross multiply. Because at the end of cross multiplying, at least you don't have fractions anymore. Okay, now that's a quadratic. And if you're going to solve a quadratic, then you have to get everything on one side, 0 on the other, and then take your pick, right? You could solve it by factoring. You could solve it by quadratic formula. I solved it by, okay, I'll see you. I solved it by factoring. If you remember, the way you do it, since that's not 1, you got to go 4 times negative 30 is negative 120. And then what are the factors of negative 120 that add up to negative 37? Negative 40, positive 3. So split up the middle term, group the first 2, group the last 2, factor each one of them, factor, negative 3/4 and 10. So that makes. Okay, and then the last, an absolute value equation, right? Same, what's the first step in solving an absolute value equation? Isolate. So subtract 1, it gives you the 8, and then you've got to undo the absolute value, right? You can't do algebra with the absolute value symbols there, so we've got to take a step that gets rid of them. The step is we set 2x minus 7 equal to positive 8, and we set it equal to negative 8, because either one will solve this. Right? If what's inside equals positive 8, then the absolute value has no effect, 8 equals 8. If what's inside equals negative 8, when you take the absolute value, it flips the sign, now it's positive 8. That's the strategy, right? And then you solve these 2 equations, get 2 answers. We're only looking for 1, and it is C. So those 4 should have been C, D, D, C. So if you look back at the package we've done so far, right, we've done 1, 2, 3, 4, 5, 7, 8, 12. What are the ones we just did here? 17, 21, 23, 24. I mean, you go back and look at those and ask yourself whether you feel comfortable you'd be able to solve that kind of problem, because that is what you're going to see on the test. Not exact same problem, but pretty darn close. Remember, you need 27 to pass. You probably need about 44 to get a pass advance. That's what you're shooting for. Okay. Okay, I'm going to get into the lesson part of it now, and I'll say that this is probably the most painful lesson of our review period. There's probably more understanding that goes into it, but, I mean, you generally don't like it that much. What can I say? But we need to, Algebra 2, yeah, if you want to turn around so you can see what's going on. Algebra 2 is generally a class where we try to expose you to a lot of different kinds of functions and the concepts of domain and range and transformations and asymptotes, things like that. And so this is kind of a summary of all the kinds of functions that we dealt with. All of the homework is going to be related to logarithms and exponentials only, but I'm just using this as the opportunity to talk about these concepts of domain and range, things like that. Okay? You ready? Trey? You ready? Okay. Okay, so the first kind of function, the one that you should have known, yeah?
How are they grading the SOL? How come you can miss 6 for pass advance and then you can
Well, they have their own, obviously it's not a linear scale. Yeah, I can't explain how they come up with their scale, but that is 400. I mean, just to take it as a straight percentage. 400 out of 600 is passed. That's about 2/3, 67%. Okay, 500 out of 600 is pass advanced. 5 out of 6 makes 83%, something like that. So that's their scale. Actually, we had a really great argument yesterday about this, about using the SOL as a test grade, which I intended to do. But I just say that, I mean, I've done this for like AP, you know, the AP, if you take an AP class, let's say AP stats. I don't know that all the classes are exactly the same. In AP statistics, in order to get the highest grade, which is a 5, right? 1, 2, 3, 4, 5, you need 63% correct, right? In order to get a 4, you need 49% correct. In order to get a 3, which is what they say is like the minimum passing, you need 37%, you know, barely a third, and you get a passing grade on the AP stats. In order to get a 2, you need 29%. So, I mean, we're taking tests along the way, and kids are taking these tests, and I'm telling you that their grades are like 30, 40, 50%, which on any kind of a normal test in high school, you fail. You fail rather miserably. So what I do is I make a linear scale that takes the AP grades or percentages and translates them into our 0 to 100 scale, where A is a 90 and a B is an 80, things like that. So the discussion was, how would we do that if we were going to do the SOLs? Well, what's the minimum passing score on the SOL? 400. What's the minimum passing score in our class? 64. Okay, so there you go. 64, or 400 equals a 64. What's the problem? Well, I'll just say that one assistant principal has a real problem. Somehow everybody should get an A if they pass the SOL, which is just, again, putting way too much emphasis and credit on these silly tests. I mean, here we are losing a whole 9 weeks over just getting ready for this test, instead of actually having slowed down the whole year and learned things better the whole way and being comfortable that, you know, we've done a good job and you're prepared for the next year. No. You know, we've got to turn everything on its head to get ready for this thing. But to me, I don't see what's the problem. If you got the minimum passing grade on the SOL, you get a minimum passing grade on the test, which for most kids that are in that category, it's probably going to help their grade. I mean, the test is usually the lowest of your quizzes, tests, homework. And so if you got that and you did better on everything else, you know, you're probably in the C range or something. They should be happy with that. I mean, right, if I don't do that, then we only have 2 tests. That'll be the only 2 tests in this whole 9 weeks, and that's going to really affect you. And honestly, yeah, I think we should. But, you know, based on all the feedback I was getting yesterday, I was like, okay, forget it. Who cares? Who cares? I mean, what do you want to say? Say, what do you want to do? Give everybody an A? Should everybody get a C because they passed the SOL? I don't know. I mean, if you got a 400, that means you passed by 1 question. And you know you guessed on a fair number of them. So let's not give too much credit here, okay? I mean, holy moly. But that's why I hate our team meetings. Okay, let's look at the kinds of functions. Right, the first kind of function, something that you should have learned about in Algebra 1, maybe you didn't talk about domain and range, but you did talk about linear, right? Linear means the graph looks like a straight line. And as long as that line has somewhat of a tilt to it, that means the domain and the range, all real numbers. Okay, these arrows go forever up and forever to the right, forever down, forever to the left. So that would be all reals. All reals. And I don't know how they might say that on a test, on the SOL. They may do something like this, where they put parentheses and say negative infinity, comma, infinity. You know, it means goes from negative infinity to the left, positive infinity to the right. Or they might do negative infinity is less than y is less than infinity. And they all mean the same thing, all real numbers, right? Now, there's actually 2 kinds of lines that don't have domain and range of all real numbers. What two lines are those? Undefined is not a line. Undefined is a slope. Horizontal and vertical, right? So, again, I remember in class saying, okay, tell me now, which one of these is vertical and which one is horizontal, right? And do it with your hands, which is it? And this is an Algebra 2 class. And half of the kids that say, what is a vertical line? Half of them are doing this, and half of them are doing that. And it's a 50-50 shot. So basically, we didn't even know what's a horizontal and vertical line, which means, I guess, you don't know what the word horizon means, okay? But that's, okay. So which one is this? Yeah. Right? Okay. So which one is this one? That's the horizontal line, right? It has a slope of 0. Not undefined. 0 is not undefined. 0 is a good number. It's right in between the negatives and the positives, right? What is the domain of that line? All real numbers. What is the range of that line? It looks like it's that line is y equals 5. What is the range? 5. 5. It's got one value, 5, right? This line is the line x equals 3. What is the domain? 3. What is the range? All real numbers. Okay? Blue. Okay, the next kind of function that we dealt with was absolute value, which has the shape of a V. It's kind of linear, right? It's got two different linear pieces that come together as a V. This is the parent function, y equals the absolute value of x. What would you say is the domain of that? All real numbers, right? This thing is going infinitely to the left and infinitely to the right, so it's all reals. Another way to think of it is, can you imagine anything that you can't plug in for x that would cause some kind of, divide by 0, your house blows up, some kind of problem there? No, you could plug in anything. It's not an issue. So that's why it's all real numbers. This one is drawn right there. What is the range? It starts at 0 and it goes up from there. So how would you say that? Okay, you could say 0 is less than or equal to y is less than or equal to infinity. You could say y is greater than or equal to 0, something like that. Okay, now, how would we shift the graph and how would it change domain and range if I did something like this? Y equals the absolute value of x minus 2 plus 3, right? What are the transformations there? Minus 2 inside of a function always means right. Plus 3 after a function always means up. Okay, did moving the graph to the right 2 change the domain? Did moving the function up 3 change the range? Sure. Yeah, now it's y greater than or equal to 3. So this would have a range of y greater than or equal to 3. But the domain, it wouldn't matter since it's already all real numbers. If you move it left or right, doesn't matter. Okay. Quadratic, right? What do you call the graph of a quadratic function? It's a parabola, right? And again, the parent function is y equals x squared. Now again, can you imagine anything that you could plug into that x that would lead to some undesired consequence? Right? So it's all real numbers. And it should, even if the graph is kind of tight, you could be sure that these arrows are going infinitely to the left, infinitely to the right, which means all reals. So what about the range? Yeah, I mean, it's just like the absolute value, right? It's y greater than or equal to 0. Okay, how would that change? How would that change if I had this? Y equals negative x plus 2 squared minus 4. What's the effect what's the effect of putting a minus in front? It flips it upside down, right? That's a flip. Okay. And what is the effect of a +2 inside the function? Left 2. And the -4 means down 4. Okay, down. So if I was going to sketch the graph, I'm going to go left 2, down 4, and then I'm going to draw it going down. Okay, what is the domain and range of that? The domain is still all real numbers, and the range is almost or equal to, right? It definitely does touch that point. Y is less than or equal to -4. Right, that's the range. Now, there was two standard forms for a quadratic function. Y equals ax squared plus bx plus c. And the other one was y equals a times x minus h squared plus k. What did the h and the k represent? The coordinates of the vertex, that point right there, or that point right there. So in fact, you can think of these values here either as transformations, shift left, down 4, or you could think of the coordinates of the vertex, right? That's when it says x plus 2, it means -2, -4, -2, -4. That's the vertex. Or it's left 2, down 4. Either way. Okay. A cubic function looks something like that. I mean, this is the parent function, y equals x cubed, as close as I could sketch it. Now, generally, a cubic function has a shape that looks like that, right? It could have two turns in it, two turning points, relative maximum, minimum, right? It either starts in negative territory and ends up in positive territory, or it could go like that, right? What would you say is the domain and range in either case? Yeah, I mean, these arrows are going infinitely to the left and right, infinitely up and down, so both of these are all reals. Right. What you notice here is because the degrees of power was 3, which is an odd number, all reals, all reals. Right? When we had the straight lines, which the degree was 1, all reals, all reals. When we had an even degree like that, then it was not all reals, all reals. So when we get to the next one, which is quartic, right? Quartic, I didn't put the parent function on there, but how many turning points would you expect to get from a quartic? You could have up to 3, right? It's 1 less than the degree or the highest power. Okay, so that's the general. 3 turning points. It either is going to start in positive territory and end in positive territory, or it could start in negative and end in negative because it's even. And then what would you say is the domain of it? The domain is still all real. The range will depend. I mean, on the one I've drawn right here, it only goes so far down. If these are every 1, let's say it would be y greater than or equal to 1/2, something like that. So remember, we were supposed to have learned about a lot of different functions, a lot of different shapes, and mostly because they expect that we might be given data, and then we might have to put the data in the calculator, draw a scatter plot, look at the data, recognize the shape, and then go to this menu in the calculator, stat, calc, and look for your function right there, right? How do you know which one to look for? Because you know the shapes of all the functions. Okay. So on this screen right here, we got linear, quadratic, cubic, quartic, right? You see all of those. And there's more if you scroll down. Now the square root function, right, the parent function is the square root of x. And this, this brings up the concept of inverse functions, right? If this is the, let me do it like this. If this is f of x, then the inverse is x squared, right? And the inverse, a function and their inverse should look like they're flips across the line y equals x, the identity function. So if I draw this, if I draw the parabola, boom, here, where's that? Come on. Something like that. Those two lines should look like they are flipped across the line y equals x. Now, does that red line, which is the x squared, look like our graph of x squared? What is the shape of the graph of a quadratic? Is that a parabola? It's half of a parabola. Because remember, you can't, a function actually doesn't have an inverse unless it's one, what you call 1-to-1, which means that both that line and that line would have to be functions. They'd have to pass the vertical line test. And if we had the entire parabola there, you know, anyways, if we had the whole parabola here, then this would have to be the whole parabola too. And the square root of x is not. It's just the positive square root. It's just this one right here. So what, if just looking at the blue line, what is the domain of that? What, x is greater than or equal to 0. What is the range? No. It's not x greater than or equal to 0. It's y greater than or equal to 0, okay? So the domain is x greater than or equal to 0. The range is y greater than or equal to 0. And it can be transformed just like all the others. Right, the cubed root, again, should look like, remember, we already had the cube on there. The cube looked like this. So that should look like it's just a flip across that line. What is the domain? Remember, what was the domain and range of a cubic function? All reals, all reals. So the domain and range of the inverse, the cubed root, should also be all reals, right? Okay. Now, exponentials, we had two kinds of exponential functions, growth and decay, right? Exponential growth has this kind of a shape, right? And exponential decay has this kind of a shape, okay? If I look at, let's say, the exponential growth, y equals 2 to the x, right? The fact that the number that's being raised to a power is bigger than 1 means it's going to grow exponentially, which means really quickly, right? Now, if you're looking at that function, is there anything you could plug into that function for x that would make the y equal 0? What if you plugged in 0? What would y equal? It would equal 1, right? Anything to the 0 power is 1. What if you plugged in positive numbers? Is 2 raised to any positive power going to equal 0? Okay, if you raise it to a negative power, that's like saying 1 over 2 to a positive power, or 1/2 to a power. Is 1/2 to any power equal to 0? No, which means that this graph, and actually both of them, cannot touch the x-axis. And so what do we call that on the graph? It's an asymptote, right? So we have an asymptote. It's the first time we came across this concept of an asymptote. And usually we draw it with a dashed or a dotted line, wherever it is, and we just have to make sure the graph looks like it comes infinitely close without touching. So these arrows are intended to look like they're going infinitely to the left and infinitely to the right, which means the domain is all real. But what is the range for both of those? Yeah. Greater than, not greater than or equal to, because it can't touch the x-axis. So got to be careful to say y greater than 0. Now, what if I had y equals 2 to the x minus 2 plus 3? What is the shift because of the minus 2 inside the function? Right 2. What is the shift because of the plus 3? Up 3, okay? Which one of those is going to move the asymptote? The up 3 is going to take the graph and move it up 3. So now where's the asymptote going to be? It's going to be here. So what would be the new range if I move the graph up 3? Y is greater than 3, right? So transformation of an exponential function up or down moves the asymptote, changes the range. It doesn't change the domain. Right? A logarithm, we learned, is the inverse of an exponential. So if I have f of x equals 2 to the x, then the inverse is log base 2 of x. So whereas the exponential had an asymptote on the x-axis, the logarithm has an asymptote on the y-axis. All right. Whereas the exponential had a domain of all real numbers, the logarithm has a range of all real numbers. They switch domains and ranges. Right? Whereas the exponential had a range of y greater than 0, the logarithm has a domain of x greater than 0. Right? So you can, looking at the graph there, that makes sense, right? X is greater than 0. It never touches the asymptote. Now this line here, if you are stuck and you just put it in your calculator to look at it, you're probably going to think, you know, that's not going infinitely up, but it is going infinitely up. It may not look like it, but it is. So you got to know that much about the functions, domains, and ranges. Okay, now if I do the same kind of, let's transform it. What if I have y equals log base 4 of x plus 3 minus 6? What is the effect of the plus 3 inside? Left 3. And the minus 6 after is down 6. Okay, which one of those moves the asymptote? It's a vertical line. So moving it up and down wouldn't change anything. But moving it left and right, it's definitely going to change it. Right, so if I move it to the left 3, what's the new domain? X is greater than negative 3. Right, that would change it. Okay, and then the last kind of graph is this inverse variation. The inverse variation looks like a number divided by x. Okay, we'll call that the parent function. And it looks like this. It has one branch there, it has one branch there. Okay. Now, if you're looking at that function there, now what would you say is the domain? X does not equal 0. Now you do have a problem. You should be able to spot it just by looking at it. If you put in x equals 0, you're dividing by 0. That's undefined. Right? So that's why this graph has an asymptote here. Right? X equals 0. And then is there anything that we can plug in for x that would make the fraction equal 0? No, that would be undefined. No, there's nothing, right? The only way for a fraction to equal 0 is the numerator equals 0. And already the numerator is 3. It's never going to equal 0. So it has an asymptote here. Okay, so if we had to do a transformation like y equals negative 1 over x minus 2 plus 1. Okay, what is the effect of the minus 2? Right 2. So you would have to take the asymptote here and move it to the right 2. And the plus 1, up 1. So you would have to take the horizontal asymptote and move it up 1. And what is the effect of the minus in front? It's a flip, right? Which means it would take this branch and it would flip it to the fourth quadrant. It would take this branch, it would flip it to the second quadrant, right? So if I was going to sketch it, right, I would sketch over 2, up 1, and then I would draw my 2 branches like this, based on those dashed lines. Okay. And a couple quick things. We have to know how to convert from exponential to logarithmic form. Right? Remember what we said about the base of the exponential is the base of the logarithm. The logarithm equals the exponent, and then the 8 is what's left. Okay? So using that as the pattern, convert that to a logarithm. Log base 4 of 16 equals the exponent of 2, right? Log base 4 of 16 equals 2. Okay, what about log base 3 of 81 equals 4? Convert to exponential. Right? The base is 3 raised to the exponent of 4 equals 81. So we should be able to go both ways on that. So we have 2 special logarithms. One is log base 10, right? It's called a common logarithm, right? That's this one on your calculator. So if you had to take a logarithm base 10, you just hit that button, and that's it, right? The other one is called the natural logarithm, and that is log base e, right? The thing that we're using to store for y. And that actually goes by ln. It's right under the log button, there's an ln button. So if you had to take a natural logarithm, if you see ln, use that, that's what it represents. Now, what if you had to take a logarithm of another base? How would you do that? Right? You would either go math, scroll to the bottom, and pick log base. That'll let you take a logarithm of any base. Okay? Enter. When you pick it, it gives you a chance to fill in whatever base you want. So you might use that to evaluate a logarithm. You might use that to graph a logarithm, which is of a different base. You could also find it by doing this. Remember when we go alpha, y equals, to find, I think we found the summation that way. Well, if you look down at the bottom, there's log base. I mean, there's at least 3 things there that we use. Absolute value, summation, log base. So if you have to do, and the homework, there is some evaluate. Okay, so if you had to evaluate that one, right, go ahead and pick the log base. Put a 2 for the base, a 16 here, and you get 4. Okay. So the homework is on page 491. It's mostly transformations of logs and exponentials, but there is a little bit of converting from one to the other, and there's a few that are evaluate, and they might have different bases. So did anybody look for that Wabbit EMU for the emulator? Yeah. So, I mean, if you need it, you could use that to evaluate.